So what we want to get in today is what's so-called the trig substitution. It's not the trig integral, it's called a trig substitution. So we're gonna have to wait until when we get into an actual problem that to really get a hang of what that is all about. Okay, so I'm going to demonstrate with one problem again. And example 1. Yes, it's all about we're evaluating integrals, right? We want to find the integral for, let's say, our function. So let's have a simple start right here. So it's a square root function. Okay? And then 1 minus 4 x squared into x. The expression itself for that integrand looks surprisingly simple, but that's dangerously complicated right there, right? I mean, dangerously complicated. It looks surprisingly simple, but a lot more complicated than we think like that, right? See, trust me, if you use the usual substitution, it's not going to work in any of that. So the idea of the trig substitution is as following. By the way, it comes out from observation. And so I learned this from the people before me. They passed it down on me, and now I pass it down on you guys. That's all. It's a technique, right? So we also have to learn from the way how they observe it. They observe that coefficient here. It's a difference between it's a difference in the square root. It's a difference, right? And then there's a constant. There's a constant. Right now it's a 1. There's a constant minus, right? And then there's another coefficient with the x squared expression again. You guys with me? So I'm going to see the 4x squared particularly as a 2x all squared. That's an observation right there. You know what I'm saying? No? So in that way, I am going to purposely substitute. It's a substitution method. It's the substitution method, but it has some specialty in it. So I'm going to substitute I'm going to let the whole 2x here. Okay? I'm going to substitute that by some cosine of theta. You guys see what I'm saying there? Okay. And you can also do the same with sine of that as well, with sine of theta as well. But it's just I don't know why. It's majority rule, I guess. It's just a bigger majority of people substituting that with cosine, even though substituting that by sine it will work as well. But so here's the thing. So it's a substitution. So right now you can see that as an x equals a 1/2 times the cosine of theta. You guys agree? Okay. But then really, at this point, I hope you guys are even more than that. So it means the dx d theta is a 1/2 minus 1/2 actually sine of theta. Do you agree? It's just the usual substitution, nothing more or less. So I'm going to rearrange my differentials here, making it so 2 dx, and actually, nope, I need to do that. So dx itself, just like that, right, equals minus 1/2 okay, sine theta d theta. You guys agree on that still? So it's just, like I said, the usual substitution. The only thing is that this substitution itself from the beginning was hard to expect, right? It was a little bit unexpected like that. Because in the beginning day, when I first introducing the substitution method, I said there's no right or wrong, right? But in here, there's a certain guideline of what to pick. There's a certain guideline for what to pick for here, for this family. But then other than that, after you pick your substitution, things work out just like the usual substitution. So now let's put the pieces together here. All right. So as far as the substitution, you got your square root expression becomes a 1 minus. So the 4x squared was understood as the 2x all squared, right? And 2x is substituted by cosine of theta. You guys with me on that? Okay. And so here I'm seeing that it's going to be a cosine square of theta. Okay. And then your dx now is substituted by negative 1/2 sine of theta. theta. Hold it all together still. All right. So now, do you recognize 1 minus cosine squared? Sine squared, right? Sine squared of theta. There you go. And so all together, and I can pull that negative 1/2 in front of my integral. So negative 1/2. Right? Then this inside the square root here is the sine square. So square root of sine squared theta, right? Times with the sine theta, d theta. And I already pulled that negative 1/2 in front. So one more algebra step right here. So square root of sine squared is going to make it just simply a sine theta, and sine theta times sine theta, right? So altogether we're looking at the sine square theta, d theta. But now when you arrive at this integral right here, then you should be able to move on, right? Because the integral for sine squared, we're going to think of that as a double angle formula, just like how we've learned just right out of the trig integral. Okay? So on my board here, I'm continuing further, right? So negative 1/2, I'm seeing this integral as 1 minus cosine, or how about 1/2 minus cosine of 2 theta over 2, okay? D theta. We good? Right. I mean, it was 1 minus cosine of 2 theta, but then all over 2, and then I purposely separated it out into 2 separate terms. Yeah, that's all. That way, for the next step right here, we have minus 1/2. Now it's just the integral over here. The first term becomes 1/2 theta. The next term right here becomes so minus cosine, so minus sine, which is 1/4, right? Sine of 2 theta. Let's see. So yes, in that way, I'm going to make it negative 1/4 theta plus 1/8 sine of 2 theta plus c. So we got the integral done, but are we done with the problem? We're not quite, right? We're going to have to bring back the original variable. So now keep in mind earlier, so back from our work right here, 2x was substituted by cosine theta, right? 2x was chosen by cosine theta. And so in that way right here, I'll think about theta itself will equals to cosine inverse, right, of 2x. You guys following? So the way it is that relationship between cosine between theta and x, right? So 2x equals cosine theta, and that means theta itself is to equal cosine inverse of 2x. Agreed? Okay. And so I'm going to bring that information back into my problem right here. So theta, 1/4, right? So theta here is a cosine inverse. Of 2x. One of that. Also 1/8. Now, how do I write sine of theta? I mean, sine of 2 theta is the same as 2 sine of theta times cosine of theta plus c. You guys can remember that? Sine of a double angle. The sine of a double angle, any double angle, right, equals 2 times sine of theta times cosine of theta. You should have had that from your previous learning, but in case that's faded away, right, then I can just briefly remind you that. Yeah.
You just remember these, right? There's not exactly a trick to.
There's also a trick to derive that, actually. You think of that sine, but then, of course, there are certain things you still have to remember, like the sine of a sum like that. Okay. So it goes sine of theta times cosine theta, okay, plus another sine of theta times cosine theta. See what I'm saying? These added up to give you that. So this identity right here you need to remember, because like sine of a sum right here, sine of x cosine of y, okay, plus sine of y cosine of x. Right, there you go. So there are a few things in tricks that you've got to remember, but that's not too many. There are not too many of them. then the rest you can derive. Saying that as consequences. Right? Now, why am I doing this in this problem right here? Because in the next step right here, and the sign itself right here, sign you always have your choice. You think of that as a square root, just like that work we've done earlier, 1 minus cosine squared. Later, see what I'm saying? No? Okay, so that's how we understand about sine. So now we have everything ready. Minus 1/4 times cosine inverse of 2x. We're on our way bringing the original variable back, right? So 2 cancel with 1/8 right here, making it 1/4. See what I'm saying? No? Okay, and then the sign here is the square root of the cosine square, but cosine itself is a 2x, right? So now that sign theta right here is the square root of 1 minus 4x squared. You guys saw it? And then we multiply with, now cosine theta is just simply 2x. So there's a 2x multiplying it, right? Let's see. So the 2x, and the 2 right here on that 2x, cancel with that 4. So our final answer, right? Our real final answer will come out being negative 1/4, right? Cosine inverse 2x plus, now that cancels, making it only a half, right? Of 1/2 x square root of 1 minus 4x squared. Let's see. You want to say no? Okay. So that example right there was just a demonstration of the idea. So now let's get into the core fundamental of what's the guideline to choose something like this. So this problem that I introduced as first right here, right? This problem right here, it stays in a family. It stays in one family. Now I want to bring it up a little bit. It stays in a family that, hey, when you have, anytime you're looking at an integral, right? And then what you have here is a square root expression, some square root expression that involves, let me roll it back here, it's an integral some function. Right? But then the f of x right here is involving the some square root in the setting that we got a constant square minus an expression square. You want to say that? Right. Notice that I'm using, so inside the square root I have a constant, right? And we see that constant as a square. And then subtract, so constant subtract and expression square, the constant subtract and the expression square. Right? That's what just happened right here in our problem. Right? You got a square root, right? Square root, and then there's a constant right there, subtract, and the expression square. That expression right here is the 2x all squared. See what I'm saying there? Okay. Any question for me on that? And so in that way, the substitution that we will be doing, now note that the x I'm using here in my generalized expression, it's a capital X I'm using in my generalized expression, right here. It's not the same x with that dx, okay? But my point is that when you're seeing, anytime your function involves some square root expression that has this constant minus an expression square right there, right? Then you can quickly substitute. You can easily substitute with the entire expression right there. The expression that you recognize as a square right there, you can always substitute that as a times cosine later. That's the guideline in here that you can use. See what I'm saying now? And it's also the same result if you let x here, that capital expression right there, equals a times sine it later. It works too. See what I'm saying now? It works too. That expression a b sine theta also work. And so that's right there explains that explain this reason why I chose back on my beginning of the problem right here. I chose you see after recognizing 4x squared here as a public square expression, right? You see this one right here is equivalent to the capital X I was talking about right there. So I'm letting that capital X, right, to equal cosine, but another truth behind the scene right here. You see your constant is a 1, right? The constant term is a 1, so recognizing that 1 as a perfect square. And 1 here is a 1 square, right? And that's why in my substitution, this is what I did right here. It really was the whole capital X equals 1 times cosine theta. You see what I'm saying now? Right? And that's a lot to realize about the work I've done there. So simply it purely was a substitution problem, but now I'm pointing out there was a certain guideline of what we substituted here. Right? So when we go in with trig substitution, right? Trig substitution, we treat that just like a substitution problem, but then there's a certain guideline of what to pick to make it work. You know what I'm saying? No? Right? So in that special form that involves any time that you have that expression square root and then a constant minus an expression being squared, right? Anytime you're seeing that, think about a trig substitution with a times cosine theta. Okay? Substitute that for the big expression that you recognize as a square. Okay? See what I mean? Right? And so now we're going to really apply that into a few problems to get more experience. Example 2. But in this example 2, I'm going to throw in a few different problems here. Okay, so part A, we've got a problem like this. How about x cubed square root of 4 minus x squared dx? All right. So when you're looking at this problem right here, do you see that nature of the square root expression that involves some constants, right? Minus some expression square right there. It's right here, right? And that's why I always said in my guideline earlier, I always said anytime it's involving, it doesn't have to be just that only one, right? As long as it's got this expression here involved somehow. So here it's involved in what way? That square root expression multiplied with some x cubed, and your overall thing is some f of x function. Right? So your whole f of x is here, but it involves this square root expression. Sounds good? No? So in that way, a couple recommendations. A couple observations here. See, I see this as 2 squared. You know what I'm saying? So your a is 2, right? That's just a little note of that. You know what I'm saying? So your expression, the expression you see as a square right here is just simply an x. You guys following? And so in that way, now after all of that, those extra notes here, and of course I'm going to have to erase that, right? I'm going to go ahead and substitute as following. I'm going to let x right here equals 2 cosine theta. Are we good? There you go. Right? And then from here, it's easy to see that dx will equals minus 2 times sine of theta, right? D theta. Technically it was a dx d theta, right? And then I did that work, and then I rearranged the differentials as well to instantly solve for the dx. You guys all with me still? Okay. And so now let's see how we put the pieces together. Okay, so this integral, right, in the next step, the x cubed didn't get a substitution. Actually, it did. Right? The x is substituted by this 2 cosine. That's why your problem becomes the 2 cosine theta all cubed, right? And then now we're in the square root, and we're looking at 4 minus, and then the 2 cosine theta all square. I'm just doing the raw substitution and putting things in, right? And then the dx here is substituted by minus 2 sine of theta, right? D theta. That way I have the 8 cosine cube theta, and then here the square root. You can see that it's a 4 minus 4 cosine square of theta, right? And then times the negative 2 sine of theta. Do you agree? We'll do that now even further. So now I can factor out that 4, right? And making it 1 minus cosine square right there. So it's 4 times sine square inside the square root, right? And then taking the square root right there. So in my next step it becomes, and I can multiply the negative 2 with the 8 altogether. So it's making it 16 minus 16 times cosine cube of theta. Okay, and then there's here we got the sine square of theta. Okay, d theta. It should have been 32. Okay. Yeah, because this here is a 2 sine theta. Okay. And then the 2 times sine theta with the that, making it sine squared, and then the negative sign with 2 times negative 2 and multiplying it with 8, it's making it negative 32 actually. All good? Right, so now in this way over here that we have, so in the next step, and this now we bring in that learning we had earlier, right? It's a cosine and sine of some power of cosine, some power of sine. This guy here is odd, right? So we separate one of that guy out. So we're gonna make it c minus 32, right? So the trig integrals learning experience is still here, and then we have cosine square theta times sine square, right? Theta times cosine theta here. Right? And so we're gonna purposely see this cosine square as minus 32, right? And then now it's 1 minus sine square theta, okay? And times sine square theta, okay? Times cosine theta. So we're gonna further substitute, right? We're gonna further substitute. Let the u be sine theta. So that means du will equals to cosine theta, d theta, and leading to that will lead to d theta will be substituted by du over cosine theta. Okay. So the integral here will turn down to be minus 32. Integral of 1 minus u squared times the u squared times a du altogether after the substitution, after all the elements here brought together. 2 different substitutions. So one substitution was to turn the x into the theta, right? And then as part of the work right here, we now realize it's a trig integral. So we've learned that, and then now we do that extra substitution right here with u equals sine theta, right? And we have to do the work here. Okay. Yes, for this problem here, it brings in 2 substitutions. Alright, and so now with that one right here, it's just a matter of, so why don't you guys go ahead and finish this integral here in terms of u for me, in terms of the u variable. So you can distribute that in, actually that's easy enough, I can just, it's negative 32, and then u squared right there, so it's over 3 u cubed, right? And then plus, now 32 over 5 u to the 5th power plus c. That continuing that to the next step right here. U was substituting for sine of theta, so we're looking at minus 32 over 3 sine cube theta, right? Then plus 32 over 5 sine to the 5th theta plus c. These are sine cube theta, sine to the 5th theta, but remember cosine theta. 2 cosine theta was defined to be x, right? You guys remember that? So that means x over 2 will be cosine theta, right? Think about a triangle like this. Or you can also have the following Pythagorean theorem. Remember that sine squared plus cosine squared always famously equals 1. And so that means in this substitution that we chose, right? And sine squared of theta plus x squared over 4, right? Has to be equal to 1. You guys remember that still? Okay. And so that means, that even means further now, and just write it up here. I've got more space. I don't want to violate this stuff. Squared theta plus x squared over 4 equals 1. In that way, I'm looking at sine squared theta will equals 1 minus x squared over 4. And then we're going to make the common denominator and all that. So in the end, sine of theta equals plus and minus the square root, right, of 1 minus x squared over 4. You know what I'm saying, no? We will choose the sine theta here to be a positive one. So you know, we choose the sine theta being a positive one. And so you can rewrite, I mean, you can re-express this as a, really as a, because you can make common denominator and all that, right? 4 minus x squared all over 4 inside the square root. So we can reduce that out as a 1/2 outside the square root and 4 minus x squared. So now what's good about all that work we did is now we can bring that and substitute it back into our expression that we have currently found for our final answer. So here it turns out being minus 32 over 3. Then there's a 1/2 square root of 4 minus x squared, right, cubed, right, plus 32 fifths, right? There's 1/2 square root of 4 minus x squared to the 5th power plus c. Okay. Yes, we're done with that. Okay. I mean, you can simplify that down a little bit, but there's no need to. We have found that integral. All right, so let's look at another one. Right, part B of our example. 8x squared, right, over square root of 49 minus x squared dx. Okay. So once again, I see there's a constant, right? There's that square root expression involved, right? This time it's involved in the denominator, right? And then there's this constant minus a square expression like that. See that? Right. So I recognize the 49 here as a 7 squared, right? So now I'm going to let x here equals 7 cosine of beta. Right? So I'm treating that entirely as a substitution problem, but it has a guideline, right? It's being guided. It's a guided substitution. Right? It has a certain guideline for it. So now, so dx, right, equals minus 7 sine theta, right? B theta. That's B. That was really, it was the dx and theta equals minus 7 theta, and then we rearrange the differentials. And now, back in the problem, right? We're looking at integral, 8 times, so x is 7 cosine theta, so we have 7 cosine theta all squared, so you guys are advanced enough. So let me just substitute that straight into a 49 cosine squared theta. How's that? That's after substituting in for the square on top. And then we're looking at the square root, right? Now it's 49 minus, and then another 49 cosine squared in the denominator. Okay. And then the dx here would be substituted by negative 7, right? Cosine, I mean sine theta. Theta. Are we good with that there? All right, so now I need your calculation helper here. So 8 times 49 times 7.
Negative 2,744.
Okay, slow it down a little bit. Negative
744.
2,744. Thank you. Right. And then the integral here turns into, and then I pull that constant coefficient out front, right? And now I have cosine squared theta over the square root of 49. So the square root here can also be thought of as 7 times the sine theta. You want to say, because after factoring out that common factor, that common factor of 49, we got a 1 minus cosine squared. You guys follow it? And then so it's 49 sine squared theta. Taking the square root gives me 7 sine theta. So that expression here, that gives me 7 sine theta. And then I still have another sine theta here to go, right? And then d theta. See what I mean? Okay. And we cancel the sine theta, right? And then this one of the 7 here cancel with that. So we're gonna roll back to the. So what's 8 times 49? Just 8 times 49.
392.
392, right? There you go. So negative. Now we've got cosine squared theta, b theta. Now we're going to use double angle and all that, right? So the point now is that doing trig substitution, we're going to bring that our problem into a trig integral, and then we use the trig integral technique that we've learned previously to handle the problem. So for this problem here, it was a square power thing. It was a square, so we're going to have to use a double angle formula again. So minus 392, right? And the interval here, we're looking at 1 plus, okay? I mean 1/2 plus cosine 2 theta, right? Over 2 theta. So we're going to integrate that by doing 392, so keep breaking that in half, so minus 2, which can be reduced theta, right? And then minus 392 over 4 with the sine 2 theta plus c.
Negative 196.
Yeah, now 196 right here. And 196 divided by 2 with that gives me 98. Yeah. Okay. Now we're going to need to bring back our original variables, right? This is how far we've gotten. We got minus 196 theta, and then minus 98 sine of 2 theta. Let's see. Let's rewrite this as 196 theta minus 98 times, and it's 2 times, so it's going to be another negative 196. Right here, sine theta times cosine theta. Let's see. But then remember, the cosine theta here, okay? I mean, cosine theta has to equals x over 7, right? And then in that, we have, think about it, we got sine square plus cosine square, right? Theta equals 1, so sine square theta, right? Plus x squared over 49, right? Has to equal 1. That leads to sine theta, right? Equals a positive. And again, I see all you guys, explanation why we chose a positive square root. Technically, it was plus minus, okay? But we choose a positive square root. And then I'll get back to you with that explanation later. 1 minus the x squared over 49. You want to do that? Okay. And so, using that sine theta equals a positive 1 over here. And by the way, this plus minus, right? And then it's just a square root of 49 minus x squared, but all over 7 outside of the square root. So it's choosing a positive square root, but here we're looking at 1/7, right? Square root of 49 minus x squared. That's for sine of x squared, right? So now in that way right here, now we're ready for putting the pieces together. Okay, so now we know that sine theta equals to this, and then cosine theta equals x over 7. Now putting that together in here, 190 minus 196. Theta here is thought of as 8. So x here is the cosine inverse, right? Of x over 7. And equals cosine inverse x over 7. That's for the first term. The next term right here is 196. Right? We think of the sine theta here as the square root of 49 minus x squared over 7. And then the cosine here, we think of that as x over 7 plus c. And these should cancel with that 196 again. So you can go ahead and cancel that out. 196 divided by 49. 8 plus inverse x equals 7, and then minus 4 x square root of 49 minus x squared plus c. We've done that problem. Okay. So that handles a lot of these problems where we have that form in the square roots involved, right? The square root of some constant minus x squared that involved there. That's how we've been doing the substitution. You want to say no? Okay. Now, so it's trig substitutions, but I still want to mention a couple more special trig integrals here, right? A few other special ones that of course it was not a required one after we learned the trigs integrals, but I still feel that they play some essential keys in your work doing trig substitution. So let's look at some other special just a few special trig integrals. Okay? So now let's look specifically at this guy right here. You got we've already learned this one here can easily be. This one here is easily, it's just a reminder, that goes straight into tangent of x plus c. You guys think about that? Recall? Because the derivative of tangent, right, goes straight into secant squared. So the derivative, the antiderivative or the integral of secant squared goes right back into tangent. Agree with that? Okay. So that's one of the special ones. So we've seen this one before, nothing much to talk about it. Okay. We're going to have another one. Let's say, what about, let's look at just secant of x. Not the secant squared. This is one single power secant of x. You want to say no? Okay. Then secant of x right here, or secant of x, this is the way how we tackle it down here. Now, think about a secant, right? Secant is famously known as a cosine of x over, the 1 over cosine, right? We want to say that. And so you can purposely turn this into a, let's multiply with another extra, so I'm going to make that a cosine of x over cosine squared of x. Nothing unusual with the algebra, right? But that means we can make that a little further into a cosine of x over that. I'm going to turn it into a 1 minus sine squared. Okay, so you know that. Okay, so let's keep it that plan. Keep the plan that way. So that means now I'm going to rewrite my integral here as cosine of x, right, over 1 minus sine squared of x dx. I'll do that observation. I'll do with that. Okay? And so in that way, now I'm going to erase this extra scratch work right here. Now to proceed further into my integral, I'm going to let u, I'm going to use a Euro substitution here. I'm going to let u equals a sine of x. So that's making it u over dx, right? So cosine of x, right? Or the du over cosine, right? Equals dx after rearranging the differentials. So here my function, my integral becomes a cosine of u. There's a 1 minus u squared, right? And then the dx here is a du over cosine of x. Okay. And so in that way, the cosine cancels away, right? Cosine cancels away, and that gives me integral. Now we got a 1 over 1 minus u squared du. Okay. And then we're gonna remember we can use that partial fraction decomposition, right? So that we can break this down to so 1 minus u squared right here. So 1 minus u times the 1 plus u when we are seeing that as a, when we put that in factor form there, right? And so we can rewrite, and the partial fraction is the formal process right here, but we can purposely rewrite this as a, it should be a 1/2, right? And then you can double check, you can quickly double check would be that by adding a common denominator, it should come back to just that 1 over the 1 minus u times 1 plus u. So now that turns into, and factoring out a 1/2 here, that turns into two separate integrals, 1 minus u plus a 1 over 1 plus u. Right? Now we're looking at 1/2. First term here goes into a natural log of absolute value of 1 minus u. and then the next one here is plus 1/2, right, of natural log of 1 plus u plus c. Are we good with that still? And this is negative sign. Okay, that. Okay. And so it will turn into, so that subtraction sign is making it no longer the addition, but it's actually, so we're factoring out 1/2, but now that becomes a logarithm of a 1 plus u over a 1 minus u. This is now a subtraction, really. It's a logarithm of 1 plus u, right? It subtracts the logarithm of 1 minus u. You know what I'm saying now? All due to that negative sign. The plus c. And now we bring it back. We bring it back to the ordinary variable. Okay, so natural log, and then I have 1 plus sine of x, right? Over 1 minus sine of x. What e. Okay. So, technically speaking, this is the antiderivative or the integral of secant of x right here. But textbooks out there do not commonly write it this way, actually. Okay? They commonly write the following. It's just a matter of now playing with the trigonometry a little more. Okay? Right? They play with the trig a little more. So, I want to swing back to this board right here. So, from what we have had up to that point there, right? Then that 1/2 of natural log, and then you got 1 plus sine of x, right, over 1 minus sine right there. Right? So just right here, right from here, we got that answer, right? And then I was about to make my way back into that formula that a lot of textbooks are writing it. So separately as a proof, think about it. Now, in trigonometry, tangent of x plus secant of x, right? This quantity right here is equal, so it's a sine of x over cosine of x plus a 1 over cosine of x. You guys agree? Right. And so with that here, we can make common denominator, right? Making it a cosine of x right here, and then 1 plus sine of x. Agree with me on that still? Okay. And so that's the same as a 1 plus sine of x all square over all square roots. There's a 1 minus sine squared of x. So now one thing I didn't pay attention to, we got a 1/2 right here, right? That's the same as a natural log, and we bring that 1/2 power in, so it's going to be a square root of x 1 minus sine of x plus c. Then this part right here, when you're inside of that square root, you can think about we can cancel that like this way. X all squared, and then 1 minus sine times 1 plus sine of this. Right. Yeah, it goes around a little bit. Now that factor here cancels one of that inside the square root. Yeah. So that's why it's making it all, which is 1 plus sine over 1 minus sine of x in the square root, which makes it really equal to this. So my point now is that the formula that people commonly use, okay, right? They're talking about the final integral for the secant of x. That's really just a natural log of tangent of x plus secant of x plus c. So two different ways of how we're writing that. So if you're writing that in terms of the sine function, it's a 1/2, right? Natural log of sine of x over the 1 minus sine of x. But then this is the more common format then. How people got that. Okay. Example 3, here we want to evaluate, right? Square root 4 plus x squared dx. Alright, so with this one right here, the reason we learn a new technique here, because if you try any of the former technique, try any of the technique prior to this point right here, then it doesn't work. Right? So we're going to need to use some trig substitution. So what I'm observing here is that this is in the form of a constant, but you can see that constant as a perfect square, and then plus with some expression being squared right there. So you got 4 pluses. The expression here is x squared, right? So it's a constant square plus an expression squared. So that's the form that we recognize right now in this problem. So this is what the trig substitution I'm doing right here. I'm gonna let the whole x right here, just that expression, which is in this case here only simply the x, right? I'm gonna let that equal to 2, because the 4 here is not up. Is seen, the 4 is understood as 2 squared. And so now I'm looking at 2 that came from that square that we recognize from that 2 that we recognize within the 4 here as a square. So 2 tangent, okay, of theta. So here in this case, continuing further with that substitution, we're looking at dx, right? D theta will equal 2 times the secant square of theta. You guys agree? Right. Or I can just rewrite it like this. So dx equals 2 theta times, 2 secant square times theta times d theta. All of that equals dx. Okay. So now our integral here will become after the substitution, we got 4, right, in the square root, 4 plus. Now, so x was substituted by 2 tangent theta. So we're looking at 2 tangent theta all squared, right? All squared. And then the dx here is substituted by 2 secant square theta, d theta. Now, the integral in the next step here becomes 4 plus 4 tangent square theta. And then times another 2 right here, secant square theta, d theta. And so in that way, now I have a common factor of 4 right here, right? So I can factor that out and pull it out of the square root. So that's making it 2 times the square root of 1 plus tangent squared of theta. And then multiply with it, the other 2 secant squared of theta. Okay. Anyone would like to have any question for me? Yeah?
Why is X and theta?
So it's just a choice that we choose here. So the strategy here is that when you recognize your you got a square root involved here, right? And inside of your square root, we in that setting where we have a constant square, right? We can recognize it as the square of a constant plus with the square of some expression. So that square of some expression here in this case is simply just the square of our variable x. Okay? And that's why I chose the variable x to equal the 2 tangent theta. And then of course right now I'm just introducing that work, and then later on I'm going to show you that generalized how we make that general substitution. Okay? And so now from trigonometry, 1 plus tangent square is actually equal to secant square as well, right? So from your trig understanding, right, 1 plus tangent square equals secant square theta. Right? So now in this case right here, I'm talking about we're substituting secant square for that expression inside the square root. Okay? Right? So in the next step, that becomes an integral, and then 2 times 2 is a 4. Right? I'm putting that 4 out front right here. So that square root is now a square root of secant square, but so square root of secant square is going to be a secant, right? And together with another secant square right here, it's making it all a secant cube of theta, right? And then times d theta. You guys good with me on that? Okay? So now for what we have right now is an integral where it's in the form of a power, right? Some power of a secant. And so we can use a little formula as follows. What we have here is, so generally speaking, right, or when you have secant of n, secant to the n of x here, you can reduce the power by, so 1 over n minus 1 times secant of, secant to the n minus 2 power of x times tangent of x. Then we're going to produce another integral n minus 2 over n minus 1 times the integral of secant to the n minus 2 of x. Yes. That's the reduction formula that I was talking about. So this formula right here, when we're using that for secant cube that we're currently working, so for secant cube of theta, right? Theta, when we're working with that. So I'm going to keep the 4 here for now. Let's open parentheses here, right? And then I have now 1 over the power for those secants here is a cube, right? So we're looking at the 3 minus 1, which is a 1/2. Sound good? Okay. 3 minus 1, which is 2, so we got a coefficient of 1/2 here times secant. So 3 minus 2 is just now a secant, right? So secant of x times tangent of x plus, and now 3 minus 2 gives me a 1. 3 minus 1 is 2, so it's another 1/2 here. And then we have an integral of just a secant of x, because n minus 2 right here means 3 minus 2. So we reduce that down to this. See what I'm saying, no? And then, by the way, this reduction formula only works for those power 2 or above. Okay, right? For those power being 2 or above. So when it's, when you are led into a secant of x to the first power right here, then you cannot use the reduction formula here anymore. Okay, but then this is the reason why I led you into that little lengthy proof earlier, because it's this integral of secant of x. So that special formula that we had, and by the way, it shouldn't be x, it should be theta here. I don't know how I magically turned that into the x here. So theta, right? Then secant of theta, d theta. But now we are having a clear direction where to go. So, and the 4 multiplying in is going to give it a 2 for the first term, and the first term is already finished, right? 2 secant theta, tangent theta, plus, and now we have a 2 times the integral, right, of secant theta. Yeah, just breaking that into little steps right here. So now for the next one right here, I'm going to go ahead and use 2 secant theta, tangent theta, right? 2 times, and then I'm going to use that special formula. So that special formula we've had earlier was a natural log, right? And then the absolute value of there's a tangent theta plus secant theta. Okay. And then just after all of that, I'm going to plus it over all C we've got. Good. So now at the end, here's my final answer. It comes out 2 secant theta times tangent theta. And we're adding 2 times natural log of tangent theta, okay, plus secant theta plus C. So we come to that. Then don't forget our beginning problem was that it was from right here. Right? We were starting with x, right, as the main variable, and somehow we magically turned into the theta. So we did that substitution. So make sure we bring it back to what it was, right? We bring back the original meaning of the original variable. So that's why now. So keep in mind the substitution was saying that x equals tangent of theta. See that? X equals tangent of theta, and then of course x squared plus 1, right, is going to equal tangent square theta plus 1. That makes it secant square theta. You guys agree?
Professor, it was 2 tangent of theta.
You're right. 2 tangent theta. Okay. That's not so bad. So in this case, but then my point is, again, squaring that, right? So x squared is going to make it 4 tangent square theta. You guys agree? And then, but then 4 tangent square theta, the tangent square plus 1 equals secant square, so you can think of the other way around. That tangent square equals, you can think that tangent square, right, of theta equals secant square theta minus 1, right? Like I'm going to substitute that into this tangent square right here. Look at it. 4 secant square theta minus 4. So that means x squared equals 4 secant square theta, right, minus 4. We good with that still? that's just the algebra of that. And then, right, any question, please? Once I erase these, it's hard to trace back. So you can think about, or I can add the 4 to both sides, right? So we've got x squared plus 4 equals 4 secant squared theta, or 1/4, right? Times x squared plus 4. Or you can write it like this. X squared over 4 plus 1, right, equals secant squared theta. So what it means now is that when we come to secant theta, it equals to the square root of, and I could have just done a 1/2 right here, right? And the square root of x squared plus 4. Okay. So some lengthy algebra, but my only purpose is now secant theta is related with x by 1/2 square root of x squared plus 4, right? I'm going to substitute that in here and in here for the secant. And then the tangent was originally, yes, x equals 2 tangent, right? So that means tangent itself equals x over 2. We're going to substitute that for these places. See what I mean? Okay. So now we're going to ready to fill it in for action here. So I have 2. The secant is a 1/2, right? Square root of x squared plus 4. And then the tangent here is an x over 2. Right? And then some cancellation is going to happen, right? And now we're looking at 2 times, add the log. Then again, just that tangent right there, we go x over 2, right? Plus, and we have another 1/2, okay, square root of the x squared plus 4. Right? And now I really need to erase all of this. So all together plus c. Then we can cancel out the 2 and 2 here. Let's do leaving the 1/2. So I have a cleaning that up a little bit. I have a x over 2, right, square root of x squared plus 4. Plus it 2 times. That's log. Here I have x. You can also write it as x plus x squared plus 4, right? All over 2 plus c. That's your final answer. Now, as a generality that we can draw out of this particular problem is that anytime you are integrating, anytime you're working with an integral that's involving, right? So anytime that you're looking at some integral that there's a square root, and then a constant square plus an expression square. The expression can just be, x squared, or it can be like 4x squared, something like that, right? The point is it's some expression squared, you know what I'm saying, no? Right? So anytime that you have something like that, right, involved, or is involved, right? Then we do the substitution that we take the whole expression x right here. See what I'm saying? That some expression that we recognize as a perfect square right there. We're going to let that equal to a, right, times tangent theta. See what I mean? To complete my sentence, you can just say when that forms, right, when the square root of a squared plus capital X all square is evolved, and we're going to substitute x equals a times tangent theta. So that's one way of how we're doing the substitution. So now let me call that example 4 here. We're going to do something. This is what I meant by having some square root of a constant square plus some expression square involved here. You see, you recognize that square root of the 4 plus 9x squared that's involved in the denominator right there. Right. The way how I see that here, that this thing is understood as some 2 squared, right? Plus with some 3x all squared. So this is the capital X I was talking about. Right. So some constant square plus some expression square, right? All right. So in that way, now what's a good choice for substitution that we can do here? So it brings about that we can perfectly choose. We're going to let the whole 3x, right? Here, now that expression, we want that to equals to tangent theta. Sounds good. So we're going to hold on to that. And then, of course, when we're taking that derivative, and we're looking at 3 dx, right? And I took the derivative, and then I also rearranged the differentials. Okay? So 3 times dx will equal to 2 times the secant squared of x, right? Times d theta. I mean, 2 secant squared theta times d theta. We're not talking about, I took the derivative, and I'm also rearranging the differentials on the 2 sides of it. And then I'm going to further solve for that dx a little further. So dx here is a 2/3, right? Secant squared theta, d theta. You guys follow it? So now this is what the integral will become. Integral, it's a 1 over, right? Then x squared, see? And right from here, let's branch it out a little bit. 3x equals 2 the tangent theta. So that means x itself is a 2/3, right? Tangent theta. We need that information to substitute for that x here. Sounds good? So now I'm looking at the 2/3, right? Tangent theta. Right? All squared. Then multiply with the square root expression. And here I'm looking at, here I have 4 times, so the 3x, I mean the 9x squared is understood as a 3x all squared, but 3x on the other hand equals 4 tangent. Right? So that means we're looking at, 2 tangents. So 2 tangent theta all squared. Okay. So that's 1 here, and then your dx here is substituted by 2/3, right? Secant squared theta d theta. So that's how I made the substitution. And so now I'm going to reduce the integral, right? So let's mix it. And then we square that, so I'm going to have a 3/2 all square over here, because that's 2/3 squared is 2/3 squared, but then it's in the denominator, so it's really a 3/2 all squared, right? And I'm putting that out front of the integral, and then that 2/3 right here, I'm going to put that out in front of the integral, right? So the integral itself, right, becomes 1 over, then we got tangent squared theta, and then multiply, and then in the denominator it's another 4 plus 4 tangent squared, right? And then times the secant squared theta as well. Doing that still. So now all together, whatever that turns out, I'm too lazy to do that math here, so it's a 3/2 squared multiplied with a 2/3 for now, and I'll get to that later. We got the secant squared theta on top, and then there's tangent squared theta, and then the square root here, see, we can factor out the 4, right? And then take the square root right there, making that another 2 in the denominator. So I could have now turn that into a times 1/2 in front here. And then your integral is a 1 plus tangent squared theta. Right? And then 1 plus tangent squared is once again that simple secant squared again. So in the end, and all of these will cancel out right now at this point, right? And the 3 squared cancel with that 3, so making it 3 over 4. So it's a 3/4, right? And then the integral, and we've got secant squared theta. Then we're looking at tangent squared theta times secant theta. Theta. And then that secant will cancel with this. 1 secant together, right? Making it extra secant left. So there's 3/4 right here. Right? And there's secant theta. And then we're looking at over tangent squared theta. Theta. All right. And so with this one right here, when you come to now this is an experience I want to add it for you guys right here, but when you are doing this trig integrals in particular that has secant and tangent involved, and then it's actually in a ratio where we got some power of tangent on top and some power of some power of secant on top, right? And then some power of tangent at the bottom. Here's a trick we can do right here. We can turn that into, now keep in mind that secant, right, over tangent square, you can rewrite this as secant is a 1 over cosine. You guys following? Right? And then the tangent here is famously known as sine over cosine, right? But then it's a square here, so tangent square in the denominator, you can actually write that as a cosine square of theta over sine square of theta. Right? That's the algebra of secant and tangent and all that, right? So since the tangent is in the denominator, so we put that as a reciprocal. And so now we can even simplify that a little bit. So the cosine tangent, the cosine got canceled, right? And that becomes a cosine. It becomes a cosine of theta over sine squared of theta. And then that means we can rewrite this as a cosine theta over sine theta times the 1 over sine theta. I purposely split it out like that. So that turns it into a cosecant theta times a cotangent theta. Is that everybody with me on that so far? Okay. So the trick here is I turn this fraction. It's a fraction again. The point is a fraction that involves a power of secant over a power of tangent. I can turn that into a product of a cosecant with some power, and multiply with a cotangent with some power. See what I'm saying? No? Okay, so that's one of the tricks there. But so now, after that quick algebra work right here, what's useful about doing that? So that means this integral work right here. Currently we've gotten to that 3/4 tangent of, integral of secant theta over tangent squared theta. We can move on into the next step, making it a 3/4, right? And then now I have a cosecant theta times cotangent theta. D theta. We look at that. And so now what's the antiderivative for this? Actually now it comes quite straightforward. What's the derivative for cosecant times cotangent? Minus 3/4. Let me write it out over here. Minus 3/4 cosecant of theta. What's the now, so in that case, we're gonna just simply need to bring back the original variable, right? The original meaning of the variable. So cosecant theta over here, but so let's go back to your work. I'm not sure if my space here has in my board here has enough space, but see 3x equals 2 tangent theta, right? So think about a triangle like this. And by the way, that means also the same as tangent theta equals 3x over 2. You guys will be on that, okay? And so in that way, think about in a right triangle setting right here, then you put your angle theta anywhere, right? Then this ratio, so tangent is opposite over the adjacent, right? So that means if tangent theta equals to 3x over 2, then we can put 3x at the opposite side from where that angle is, and then the 2 is down here. So that means the hypotenuse has to be the square root of, so 2 squared is a 4 plus 3x all squared is a 9x squared. Okay. So in that way right here, cosecant is the reciprocal of a sine, right? Cosecant is sine over it's 1 over sine, right? So that means back to this one is negative root over 4. Cosecant now is going to be so sine is opposite over hypotenuse, but now it's going to be hypotenuse over the opposite. That's cosecant. Now I have square root of 4 plus 9x squared over 3x plus c. Right? So now we are ready to just cancel out that those 3's again. So my final answer in the next board that can be written down. So now we're ready for including that answer. So now the integral from the beginning, we got that x squared in the denominator times the square root of 4 plus 9x squared, right? After all that work, that came out being minus square root of 4 plus 9x squared all over, that's a 4x plus c. Now our work. Integral x cubed times the square root of 1 plus the 49 x squared. Right? Okay. Go ahead and spend some time writing it down. All right, so now getting into this, once again, starting with the, see, it's involving a square root of a constant, and we can recognize it as a square, a constant square plus with some square expression right here. So think about that 1 plus 4x squared here. So I see that as this is the same as a 1 squared, right? Plus a 2x all squared. That's how we feel that. Okay? So in that way, now I'm going to choose my substitutions, right? So I'm going to let 2x be 1 times tangent of theta. So that's just tangent theta. Okay? So 2x equals tangent theta. Right? And so from that way right here, yes, we're looking at, see, 2 times, or one more step right here, x equals to a 1/2 times tangent theta. So the x theta will equals 1/2 times the secant square. But then I'm going to rearrange the differential. So we have a 1/2 secant square theta to d theta. So that's after I took the derivative and rearranged the differentials. Okay. And so now the integral is ready, right? We can, so that's substituted by. So the x here is substituted by 1/2 tangent. So now that becomes a 1/2 tangent theta all cubed, right? And I'm multiplying with the square root expression. And then we have a 1 plus, and then the 4x squared here is substituted by the tangent square, right? And then the dx here is substituted by a 1/2 secant square theta. Right, that's how the substitution falls out. Okay. So I'm putting it in places. Everybody doing okay with that so far? And so in this way right here, there are a few algebra work that we can do right here. So the 1/2 here multiplied with because this is a 1/2 all cubed, right? And multiplied with a tangent cube, so 1/2 all cubed is a 1/8. Multiplied with another 1/2 right here, right? That makes it all together a 1/16, and I'm going to pull that 1/16 in front. Right, so now we have left behind with the tangent cube, right, of theta. Now, 1 plus tangent square is making it a secant square right here, right? So make a note of that. That becomes a secant square, right? But secant square inside of the square root, you're going to reduce that down to just a secant, right? And then secant is multiplied with another secant square right here. You guys feel that? So that gives me a secant cube, right? Theta. Right? Now, this problem right here brings you into a trig integral where you got tangent, a power up tangent and a power up secant, and they're both odd right here. Okay, a power up secant and a power up tangent. So a little bit unlike the earlier one, it was a power up secant over a power up tangent. Here it's a product, right, of the power up secant and a power up tangent. It's both odd. So let me introduce this quick little trig right here. This little experience right here, you can use anytime. Since they're both odd right here, 1/16, right? Integral, I'm going to purposely isolate out. So now I'm going to produce tangent square theta times secant square theta, and I'm going to multiply with tangent. Or how about a secant theta times tangent theta? You good with that so far? Okay. So I took advantage of that measure of the secant being odd, right? Actually, the tangent and the secant both being odd together. So I separate out one factor from each. That's good. So now in that way, here's what I'm doing. The tangent, and also note further, the tangent itself here can be understood as it's a secant square, right? -1. That's how you can always think about a tangent square. It's another famous trig identity. Okay? So that means the integral now in the next step becomes a 1/16 integral, and then we got the secant square theta -1 times the other additional secant square of theta. Right? And then we having now the secant of theta times the cotangent of theta, right? Times d theta. So we look at that, no? Right. And then so here I'm going to do a little bit of a u substitution. I'm doing a little bit of a u substitution. So I'm going to let u equal the secant of theta. Now that makes it du has to equal, right? Du has to equal the, right? What's the derivative for secant? It's secant square, secant times a tangent, right? And then that's multiplied with d theta. Think about, I took the derivative and I rearranged the differentials. So now I found a substitution. All of that entire secant theta, tangent theta times d theta is all this, which can be substituted eventually for du, right? And then every secant here can be substituted by a u right here. So the integral in the next step becomes 1 over 16, right? And we got now u squared minus 1 times a u squared all du. Okay? So all of a sudden we have turned that problem into something a lot simpler, completely in terms of u, that we can just integrate that to my term. You guys feel that still? So in the next step here, right at that 116, the integral u squared minus 1 times u squared du, right? And we can just distribute that u squared here, making it 116, right? And then the integral of u to the fourth minus u squared du, and this now is surprisingly simple, right? It gets me, so it's going to be now we get ready for that. 116, right? And multiply with a 5, so that's making it 1 over 80 u to the fifth power. You guys follow it? And minus, right? And then 1 over 48, right? Times u to the third power plus a or the c. And then now we're going to return, we're going to bring back the secant variable over here, because u is the substitution for secant of theta, right? So it's a 1 over 80 times the secant to the fifth of theta, right? Minus, and then now I have a 1 over 48 times the secant to the third of theta plus c. And of course, we still shouldn't be happy with this answer, because our original problem was in terms of x, right? It was that x cubed times the square root expression in terms of x. Everything was completely in terms of x previously. That was our beginning point. See what I'm saying? No? And so, in that way, now we're moving over to the next step here. So, think about that triangle again. So, back at that substitution point, that substituted point, so 2x, right, equals the tangent theta, right? And that means, and you can think of this as what, 2x over 1, right, equals tangent theta. So think about that right triangle over here. That's the right angle, and wherever you put your angle theta is, so this is opposites, right? This is adjacent right here. This is hypotenuse. So you can think about if it's tangent theta equals 2x over 1, then that means you can put the 2x here, and there's a 1 right there. Are we good with that? And so the hypotenuse now has to turn out being a 1 plus a 4x squared, right? It's right by the Pythagorean theorem. And so in that way, right here, secant is 1 over cosine, right? Secant is 1 over cosine. But 1 over cosine means what? It's the reciprocal of cosine. So cosine in the triangle means what? Adjacent over hypotenuse. But now when it's the opposite way, then it's just hypotenuse over adjacent, which is just that expression itself is over 1, right? So now I'm talking about that means secant theta is simply just the square root expression of 1 plus 4x squared. That's how it happens. So now we're ready to bring this back and substitute it back into our third integral worker here. So now it becomes 1 over 80, right? And then secant, so the square root to the fifth. Okay, so square root of 1 plus 4x squared all to the fifth, right? And we're looking at minus subtracting another, so 1 over 48, right? Times the square root expression of 1 plus 4x squared, right? To the cube power plus c.
squared.
Thank you. That's correct. I should have written. Thank you. So it should have fit. So technically, at this point, we're done with our integral. But then be aware that in case sometimes you are asked to simplify your final expression a little bit, right? So if the instruction was saying do not simplify your answer, then you can stop right there, just fine. Right? Then if you ask to simplify it a little bit, then well, the fifth power here is making it. So it's making it with the coefficient 180 right here. We have 1 plus 4x all squared, and then multiply with the square root of 1 plus 4x squared. Okay. You guys can double check my algebra on that. And then subtracting 1 over 48 and the cubic on that, the square root is going to make it just simply 1 plus 4x squared with no power. And then multiply with 1 plus 4x squared. Okay. And then we can even factor out that square root if you would like to. But that's another way of writing it. Right. So now the last style for trig substitution I want to introduce. Another one I want to bring up here is 5. Okay. Let's just evaluate one of them. I want you to be aware that this one here is not 4 minus x squared, it's x squared minus 4. Right? It's different with the, so don't rush into substituting with the cosine actually. No? Because the cosine was, you see, we are through with this. If it was 4 minus x squared in the square root, right? And yes, we're gonna substitute with the cosine, right? But this case is different. See, anytime we deal with difference, it's tricky in the sense that the order of the difference matters, right? So now we're looking at some expression square, subtract a constant square. See what I'm saying now? So right from this, let me just introduce it here. I'm seeing this as a 4 square. I mean 4 is a 2 square right there. So x squared minus 2 squared. But I'm going to substitute. Actually, I'm going to substitute x right equal to 2 secant later. And then all due to the reasons. So first of all, and right now it's just I'm introducing the substitution I'm using right here. It's just a substitution I'm introducing. And so right now I see that as a 2 squared here, right? And then that is just some, of course, it's some expression being squared, right? And we're subtracting the 2 expression like that. So right now, if you're asking me why I'm doing that, you will get more of the reason later why. But right now, seeing that simply as a substitution problem, right? It's just something that I chose to substitute. Okay? And I'm pointing out for everyone. That also means that x over 2, right, equals secant of later. Keep that in mind for some other purposes later. But when x equals 2 times secant theta, then we can take the derivative, and so making it dx, right, equals 2 secant theta times tangent theta, right? And then think about, I took the derivative and I rearranged the differential, so that means we can multiply the d theta over there, okay, on the right-hand side. Are we good with that still? Okay. And so now in this way over here, I'm ready for the substitution. I'm putting in these substitutions we're looking at. So there's a square root, right? So x was substituted by 2 times secant theta. So I have 2 times secant theta, right? All squared minus 4, right? And then the dx here is substituted by 2 times secant theta times tangent theta, right? D theta, right? And so that's making it here. So one more step, I'm writing it down carefully. We're looking at 4 secant squared theta, right? Minus 4, then multiply with a 2 secant theta tangent theta, right? D theta. Then you can factor out that 4 here, and so bringing it outside the square root, it becomes a 2. So we're looking at now, and together with the other 2 right there, it's making it all together is 4, right? And then now I have a secant square theta. Secant square theta minus 1 right there, right? Times secant theta times tangent theta. D theta. We're good with that still. And then again, you can remind yourself that the secant square minus 1 is famously known to equal tangent square, right? Later. So that integral in the end, all of these. So in the next step, my integrals can become, I can pull that coefficient 4 out front. Now we're looking at tangent square, but in the square root, it's giving it tangent theta times now secant theta, okay, times tangent theta. Right? Theta. It becomes a, right here, becomes a, now I have a tangent square, right? Theta times secant theta. Now with this one right here, it's similar to the earlier problem that we've done, but see, again, it brings you into a situation where you've got a product of a power of tangent, right, with a power of secant. But this time, in this product right here, the power on the tangent specifically is even. You see what I'm saying? No? The power on the tangent is even. So this is the trick that we can do right here. We can purposely rewrite that. Tangent square, right? As now it's a secant square theta minus 1, right? And then multiply with the extra secant from the previous step. Yeah. Okay. Multiply with 4. Now I'm going to distribute. Now we're not going to do substitution, but I'm going to distribute the secant here for each term. Then sounds good. Okay. So now I'm going to move over to the other board. So currently at this step right here, we're at 4, right, times the secant square theta minus 1, and that's a secant of theta. Now in my next step, I can bring in, multiply in that secant. I'm looking at secant cube theta minus secant theta. Right? So I'm going to turn that into 2 separate terms here. So one of them is a 4, okay, secant cube of theta minus, and the other one is integral, okay, 4 integral secant theta. You all good? Okay. I'm holding on to this one. Okay, I'm holding on to that one. Now, back in the earlier lecture, I showed a power reduction formula, right? A reduction formula for this secant cube right here. So let me remind everyone. Right. So as a reminder, when you have secant, right, to the n of x dx, some power n, okay, right? You can use the following formula. It's 1 over n minus 1 times secant n minus 2 to the n minus 2 x times tangent of x, right? Plus, and then we have n minus 2 over n minus 1, right? And these formulas, I never have to remember them and say, but you don't have to remember these. I mean, a pocket reference to carry them around everywhere you go. And so with that particular one, I'm going to use, because right, and these reduction formula is only valid for the power of n starting at 2, right? 2 or higher. That's why don't use your reduction formula for this guy right here, right? You know what I'm saying? No? Okay. It's now specifically for this secant cube, I'm doing the following. Now I need a lot of space right here, so it's going to be 4, right? Times, and now I'm going to open a parenthesis here. So cubic, so it's going to be a 1 over 2, right, for n minus 1, that's following, right? Raised to the power of secant of theta times tangent theta. It's just secant of power plus, right? Plus power again, tangent theta, and then plus, now we're looking at a, so that's a 1, so n is 3 minus 2, so that's going to be a 1 half, right? 1 half times the secant of theta, okay, to the first power theta, d theta, okay? Holding that the parentheses, and we're subtracting 4 times the earlier integral here. It's a secant of theta, d theta. Good with that so far. And then I'm going to distribute that 4 here, right? For each term, making it so the first term becomes just 2 secant theta, tangent theta. Right? next term here becomes a 2, right? Secant theta e theta minus the extra 4 secant theta e theta. So now these two are like terms, right? And we have that formula we learned the other day. Okay? It's not the reduction formula, but it's really just that pre-derived work with that. But now, by the way, secant theta is tangent theta, right? Plus, actually no more plus, minus 2, right? The integral of secant theta. There. Now, our final answer here comes out. So it's going to be 2 secant theta tangent theta. Right? And we're subtracting. Now, you guys recall from last time what we did with the integral for secant theta? It's the logarithm of secant theta plus tangent theta. Yes, right? 2 times logarithm of theta plus tangent theta plus c. So in terms of theta, then we're done right now in terms of theta. But then once again, we definitely want to bring it back to the old original variable, right? And so recall for yourself. X was 2 secant theta. And furthermore, it's x over 2 equals secant theta. But secant theta here means it's a 1 over cosine, right? Keep that in mind. So that further means what? That further means cosine of theta has to equals 2 over x. You guys good with me on that? Okay. And so in that way, in the triangle right there, wherever you want to put the right angle, so theta is some of the smaller angle, right? And so in that way, see, you can put 2 here, x here. X has to be the hypotenuse, right? Right. And then now we're looking at the square roots here. That's the remaining side here has to be the square root of x squared minus 4. We'll look at that. So now we're ready for putting all the pieces together. So that means, so right from the picture right here, the secant theta, anyway you see secant theta, it has to be what? It has to be, secant was what? 1 over cosine, right? 1 over cosine, the cosine was, so it's going to be, well, just like that. We already have that, right? So it's x over 2, but tangent, right from the picture right here. Okay. Has to be opposites. Right? X squared minus 4 over 2. Right? So now I'm ready to bring it back into the picture right here. This board right here. All right. So after so much work done, 2 times secant of x was secant theta was x over 2. Tangent was square root of x squared minus 4 over 2. Right, that was outside of the logarithm. So now minus 2 times logarithm, and then the secant was a x over 2. Right, and the tangent was a square root of x squared minus 4 all over 2. Right, so in the end, we can cancel a few of these coefficients and making it 1/2, right? X square root of x squared minus 4, right? Minus a 2 times natural log. And then here I have, you can, and here's the one next thing that's really nice here. Okay, how do I write this? You can write this as x squared minus 4, right? X plus square root of x squared minus 4 all over 2. And then plus a c. You guys following? It was originally these 2 separate terms, right? But we can combine like terms and making them 1. But now, do you notice there's a fraction nature in here? There's a fraction nature right in your logarithm. So you can make that. You can turn that into. So it's a 1/2 x square root of x squared minus 4. Right? We're subtracting 2 natural log of the x plus square root of x squared minus 4. Okay? And then minus another, actually plus a 2 times natural log of 2. And then plus c. Agree? Okay, so how did that happen? Because It's all due to that logarithm of a function, right? It's the same as the log numerator subtract log of the denominator. See what I'm saying? That, okay. And so in that way, right there, I split it out into two separate ones. But then there's a subtraction inside. That's why distributing that -2, it becomes a plus, right? And then here's another nice algebra trick. It's all about algebra. You can all include all of that as one big C. There's a 2 natural log. 2 is just another constant, isn't it? And so all together, you can just write your entire 2 natural log of 2 plus C right here is just one huge C right here. And you're done for your problem. Okay? That's what it is. All right. So then that concludes our lessons on all of the trig substitution problem like that. But so the generality that we can see right through this problem is that the expression that stays in, see, some expression doesn't have to be just single x, okay? That's minus a constant square right there. Then you can always let that x equals the a times the secant of theta. Okay. Okay? And so, for example, if you are looking at an expression like that, sometimes that happens. Say, quick example, like we got the square root of a 9x squared there, and then minus a 4, for example. Then you see this as a square root of a 3x, right? All squared minus a 2 all squared. See what I mean? And so you're gonna, in that case, you're gonna let x, right? I mean, you're gonna let 3x equals 2 secant theta. That's what I mean right there. Okay. The last thing I wanna mention for you guys before we conclude out this topic on trig substitutions, and this is something that I've owed you guys for a little while. Because a lot of times when we come to taking the square roots along here, I mean, Matt, you raise a question like, how come I ignore the negative square roots with that? So it's all due to this. So as a generality here, what we've been through, you know, and then along summarizing that, I should be able to point out. But this is what we've done when it was an a square, a constant square, right, minus an expression square in the square root. So anytime that involved, right, then yes, we've been doing the substitution. So as a separate column right here, the substitution that's that's guided here is going to be the whole x right here, right? We're going to let that equal to a times the cosine theta. But see, doing this right here, it kind of requires that we need to have, because the idea now is that the x and the theta has the inverse relationship. See what I'm saying now? So in that way, to have this, the properly satisfied, we can only take this relationship where the angle theta itself falls anywhere from minus pi over 2 to pi over 2. That's the idea right there. Okay? And so think about it. For theta being on the anywhere from minus pi over 2, right, to pi over 2 on top of here, the cosine values will always turn out positive. Am I correct? And that's why back in those days when they was doing things about the sine square, right, was using sine square plus cosine square, theta equals 1, and then sometimes I need to solve for sine square, for example, whatever that is, right, or cosine square. I need to ensure I take the positive one, especially it's a sine square over here. So sine square, right, or actually the sine, right, sine of theta will be indeed plus and minus square root of 1 minus cosine. Okay? This is in between 0 and pi. That's for the cosine. Okay? So with that way right here, your circle, your semicircle looks like this. Sorry about that. Okay? It goes from 0 to pi. Okay? And so that's why now in that zone right here, then taking the square root right there, right, to get sine, then of course anywhere here your sine is positive, right? See what I mean? And that's why I had to take just the positive square root for that. Right? And then now when you do that other substitution right here, when it was square root, that of x squared plus some constant square over here. We were doing capital X to equals a times the tangent theta. And so that here requires you to set your theta only anywhere from, see, I got it misplaced earlier, minus pi over 2 to pi over 2 right here. See what I'm saying up? Okay. And then with this last one right here, it's a little confusing, but a lot of time we just assume the, I mean, that's just something to be aware about. But the secant that we've been just now learning, right? Yes, we let x equals to a times the secant theta. Okay? Right. We got either. That's the one that I never bothered memorizing it myself. Right. That's the one. Or we have another one over here. 2 pi 2 2. Pi 3 5 2. Right. So we're talking about on the unit circle, either we only got first quadrant, right? Or we in this those 2 quadrants for your angle theta. Okay. That's just to fulfill the inverse relationship requirements. Okay.